Now, if you remember, the last thing we were discussing were the rotation matrices and the eigenvalues of rotation operator. We were looking at, we started from this commutation relation, Jx, Jy is equal to I h bar, sorry, Jz, and we defined two operators, J plus and J minus, which were nothing but Jx plus or minus I Jy, such that we looked at their commutation relations and we found out that the commutator of this J plus minus with Jz was nothing but minus or plus h bar Jz, J plus or minus. It was just like the annihilation and creation operators we had when we were looking at the harmonic oscillator. So if you remember, in the harmonic oscillator case, we had the H commutator with A was minus H bar A, and H commutator with A dagger was plus H bar A dagger. So we have this operator. When we looked at the commutator with the Hamiltonian, we obtained the same operator with a coefficient. And that coefficient was nothing but how much that operator changed the eigenvalue. Well, it is just like that in the case of it was just like that in the case of the rotation operators. We had this J plus and minus commutator with Jz was nothing but the original operator J plus minus with some coefficient which determined how the eigenvalue of Jz changes. And we then looked at we also had this J squared operator and its commutator with any of the rotation generators. This was 0. So since J squared and any of the Ji's, they commute, we can just diagonalize them at the same time. But since different Ji's, they do not commute with each other, we cannot diagonalize all the three components at the same time. So at most what we can do is we can choose J squared to diagonalize and one of the J operators, and which we chose to be the Jz. That's just the convention. And then we looked at, okay, so if this is the case, we started with the common eigenvalues of J squared and Jz. Okay, so this was J squared, this was A times AB, and Jz acting on this AB, it was B times AB. And then we show that A squared, A should be larger than A is larger than B squared, which, I mean, this we derived from the fact that J squared was equal to J plus J minus J minus J plus 1/2 plus Jz squared. The operator in parentheses is always positive, so the eigenvalue of J squared, the expectation value of J squared is always larger than or equal to the expectation value of Jz squared, which in an eigenstate, this just means that A is larger than or equal to B squared. But this also means that the B has to be between or equal to minus A and A. Well, we don't yet know whether B can be equal to A or not, but then we show that the A was equal to B max times B max plus H bar. Do you remember? Or do you want me to repeat? And we also show that the minimum possible value of B was equal to minus B max. So B max, we just changed its name so that we get rid of these factors of H bar. This was H bar times M. B is B is h bar times m, B max is h bar times L, so m takes values between minus L and L, and A was h bar squared L plus 1. So these were the eigenvalues, and we have the corresponding eigenvectors. And basically this is where we had left. At this moment, we didn't have any condition on L though. I mean, the only thing we know is that A or M should change between minus L and L. We don't know whether L should be integer, half integer, or any real value. Now the constraint that L should be at least half integer, not necessarily always an integer, but a half integer, comes from the observation that, well, you start from the eigenstate LL. You lower the Jz eigenvalue by 1. You can keep lowering L, and eventually you should be reaching minus L. If you don't reach minus L, you just keep lowering it. And then the eigenvalue of Jz can take larger values than the eigenvalue of J squared, which shouldn't happen. Now this lowering of M values happens at integer steps. So L and minus L should differ by an integer. So here we should be reaching from L to minus L. Well, we reach in 2L plus 1 steps. Well, the number of steps, it should be an integer. So 2L plus 1 should be just some n, which is an integer, which tells us that L can be 1/2, 1, well, 0, 1/2, 1, 3/2, etc. There's no condition that L should be integer. It can also be half integers. The only condition we have is that 2L plus 1 should be an integer. And this is where we had left. Well, for example, we already know one case where L can be 1/2. The spin 1/2 particles, like the silver atoms. That's spin 1/2. Electrons are spin 1/2. Are all values of L realized in nature? That's another question. We know L is equal to 0 cases, spinless particles, no angular momentum. L is equal to 1/2 is spin 1/2 particles. L is equal to 1, we have just like L is equal to 1 vectors. We had already seen that when we were looking at rotation, generator of rotations in 3-dimensional space. We calculated J squared, and if you remember, we found out that J squared was just 2 h bar squared for vectors in real space. So that is a vector. Spin 3/2 particles we have observed. There doesn't seem, and in a moment we will see the orbital angular momentum. There doesn't seem to be any limit on the orbital angular momentum. So practically all of them, in principle, is possible to create. In real life, well, I mean, we just observed a finite number of particles. But at least there doesn't seem to be any reason to believe that any of these numbers are not allowed in nature. Now, let's look at one more thing. Eventually, we will be looking at the matrix representation, but to calculate the matrix representation, we also need to determine how does Jx and Jy act on my eigenstates. We kind of already know how the J squared and Jz, how their matrix representation looks like, because we had already calculated their possible eigenvalues. But to calculate Jx and Jy, we still need a bit more work. If you remember, J squared, J plus minus, they were defined in terms of Jx plus or minus I Jy. So Jx, we can write it as J plus plus J minus over 2. And Jy is J plus minus Jy over 2i. So if we know how oops, sorry, this is not jy, it is j minus. So if we can write the matrix representation of j plus j minus, then we can write the matrix representation of jx and jy. Well, let's see. We already know how jx, almost how these j plus and j minuses act on the eigenstates. If we start from j plus acting on, let's say, Lm, we know that this is proportional to Lm plus 1. It raises m by 1 with some coefficient. Let's say this is for Lm. And similarly, j minus acting on Lm, they just give us Lm minus 1 with some coefficient. And these coefficients basically are nothing but the matrix elements of j plus and j minus. Those are the things we need to determine now. Well, we can determine them by expressing j squared in terms of j plus and j minus. If you remember, j squared was just j plus j minus j minus j plus multiplied by 1/2 plus jz squared. We had already also calculated the commutator of j plus and j minus, which was do you remember? Well, let's calculate it if you don't remember. Jx plus I jy, jx minus I jy. This is equal to minus I, the commutator of jx and jy is jz, I jz, I h bar jz, plus I, the commutator of jy and jx is minus I jz, minus I h bar. So this is nothing but twice h bar jz. So which basically tells me that j plus j minus is equal to twice h bar jz plus j minus j plus. So which allows me to write j squared as j minus j plus h bar jz plus jz squared. Now let's look at the matrix element of j squared between Lm states. On one hand, we already know that this is equal to h bar squared L plus 1. Because we know that Lm state is an eigenvalue or eigenvector of eigenket of j squared. But on the other hand, this is j squared. This matrix element is the matrix element of j minus j plus h bar jz plus jz squared Lm. So this should be equal to h bar squared L plus 1. Well, we know how jz acts on these states, and keep in mind that j minus is nothing but j plus dagger. And this is equal to, plus h bar squared m plus h bar squared m squared should be equal to h bar squared L plus 1. Well, this is nothing but the magnitude of j plus Lm squared. We are just multiplying it with its dagger. This should be equal to h bar squared L plus 1 minus m m plus 1. So we are almost done. J plus Lm, this is nothing but C plus Lm, Lm plus 1, magnitude squared, but the magnitude of Lm plus 1 is just 1. So this tells me that C plus Lm is equal to h bar square root of L plus 1 minus m plus 1. Up to a phase, which we choose to be real, 0. You see, we only know the magnitude of C plus. We don't know whether it's a complex number or not. But it's just up to us in our choice of the base functions. So we just choose it to be real, and hence C plus Lm is h bar. If you just factorize it, that factor is L minus m, L plus m plus 1. So now we know how J plus acts. Well, J minus you can basically do the same thing. The only difference in this derivation is that instead of writing J plus J minus in terms of J minus J plus, you just write J minus J plus in terms of J plus J minus. You just repeat exactly the same derivation. And at the end of the day, you would get J minus here this is Lm plus 1. This is h bar square root of L plus m, L minus m plus 1. So this is how these are basically the matrix element of J plus and J minus. And if you look at the matrix element of J plus, for example, how J plus acts on Lm kit, if m is equal to L, that should be the maximum value of m. If m is equal to L, this factor just gives us 0, as it should. If you try to increase m beyond its maximum possible value, it just gives you 0. And similarly, if you look at how the J minus acts, well, if m is equal to minus L, that is the lowest possible value. If you try to lower it even further, since m is equal to minus L, it just becomes 0. Again, you cannot go below the minimum possible value of m, and you cannot go above the maximum possible value of m. Well, let's write the matrix elements. At least let's say for L is equal to 1. Let's start with J plus. J plus 1, 1. This is what is this? 0. J plus 1, 0. It is 1, 1. What is the coefficient? Square root of 2h bar. I'll just look at this expression. M is equal to 0. L is equal to 1, so 1 minus 0, 1 plus 0 plus 1. Let me write it explicitly. This is h bar, square root of 1 minus 0, 1 plus 0 plus 1, 1, 1, or square root of 2h bar, 1, 1. And similarly, j plus of 1 minus 1, this is h bar, square root of 1 minus 1, 1 plus minus 1 plus 1, 1, 0. So this is again square root of 2h bar, 1, 0. So we can just, if we denote 1, 1 by 1, 0, 0, 1, 0 by the column matrix 0, 1, 0, and 1 minus 1 by the column matrix 0, 0, 1, then J plus matrix becomes 0, 0, 0, square root of 2h bar, 0, 0, 0, square root of 2h bar, 0. This is our J plus. We can look for J minus. Now J minus acting on 1, 1. Here are the definitions. This is equal to h bar, square root of 1 plus 1, 1 minus 1 plus 1, 1, 0. This is square root of 2h bar, 1, 0. J minus acting on 1, 0. This is h bar, 1 plus 0, 1 minus 0 plus 1, 1 minus 1. This is again square root of 2h bar, 1 minus 1. And J minus acting on 1 minus 1, this is 0. So we can just straight away write the matrix element, matrix representation of J minus. This time it will be 0, 0, 0, square root of 2h bar, 0, 0. I think I made a small mistake. Okay. This one is the transpose of this one. Let's check whether it's the transpose or not. J plus, this matrix multiplying 0 square root of 2h bar 0, 0, 0 square root of 2h bar, 0, 0, 0, multiplying 0, 1, 0. This is square root of 2h bar, 1, 0, 0. So this is J plus. And this is J minus. So this matrix let's multiply this with 0, 1, 0. You see this is nothing but 1, 0 ket. This is equal to, well, the first column is 0. The second column is again 0. The third column is square root of 2 h bar. But this is nothing but square root of 2 h bar times 1 minus 1. So it's the j minus. And in fact, for arbitrary L, you can just construct the corresponding matrices. Now the last thing, we have the jx and j minus. Let's just start with jx. This was equal to j plus j minus over 2, which is 1 over 2, 0, 0, 0, square root of 2 h bar 0, 0, 0, square root of 2 h bar 0, plus 0, 0, 0, no. Square root of 2 h bar 0, 0, 0, square root of 2 h bar 0, 0, 0, 1 over h bar over square root of 2, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0. This is our jx. So we have the matrices, matrix representation of our operators also. Now, any questions up to this point? Now we will look at the orbital angular momentum next. I mean, you are probably more familiar with that one. I mean, up to this point, we don't know what these J's are. We only know how they act on our Hilbert space. We don't know whether we can write them as differential operators or not. It will turn out that sometimes we can, sometimes we cannot. Yes. Well, for the time being, we are considering rotations in general, not very really specific to a specific problem. But what we know most of the time is that, let's see, h squared and j squared, most of the time they commute. And, well, not h squared, h. And h and ji, they also commute. Well, what this means is that the angular momentum will be conserved all the time. So, for example, let's see, this is more important, especially in particle physics, for example, when you are looking at a decay of a particle or a scattering of a particle, which conserve the angular momentum. Let's say initially your particle has spin 1, so in the final state it should also have spin 1. Now, it might be that the particles will go in a different direction. So the scattering amplitude, we will be able to write them in the form Lm prime. Prime. M prime, meaning that initially it has some m in this direction, finally it will have some m prime in the other direction. So what is the transition amplitude? What is the probability for such a process? Well, in general, we don't know without looking at the Hamiltonian. We don't know how the angular distribution will be. But if there is rotational symmetry, we can tell this one. We can write this out explicitly. Now, how will we do that? Well, let me just wait a bit more. You see, in the final state, let's say it has a spin m prime in the n direction. Now we had already seen how we can write this Lm prime. This is nothing but the state Lm rotated by some rotation. So the amplitude for our transition from an initial state, let's say Lm, to a final state Lm prime, but this time in the n direction, this will be, let's say, proportional to, we still don't know what the radial dependence are, but we know how the angular dependence will be. So this will be Lm prime Lm. Well, this is the initial spin or initial angular momentum, but if the interactions are conserving angular momentum, it should still be in the same Lm state. But we are observing it in the Lm prime state in a different direction. So this is the amplitude for that probability. You see, you started with a system that has a spin in this direction. And at the end of the processes, whatever is going on, you are observing a spin in that direction. So the question is, what is the amplitude? Now, if the angular momentum is conserved, which in general is conserved unless you have some external influences on your system, if your system starts in this state, it will always stay in that state. So after all the processes, it is still in exactly that state. But you're observing in this state, so the question is, what is the amplitude? Well, the amplitude is nothing but the inner product of this state with that state. So it is what I have written over there. But that state is nothing but Lm prime. Let me put the dagger. Lm. So the question is now, what are those matrix elements of the rotation operator? Now in a moment, well, I don't know whether we will do it today, but on Wednesday we will also see what happens in the case of a rotational symmetric Schrödinger equation. Well, for the time being, the only thing we care about is the rotation. How do the rotations behave? I didn't yet separate the spin and angular momentum yet.
Peki şu an rotation dediğiniz şey, yani sonuçta coin particle var, söz ediyoruz. Biraz önce söylediklerinizden yanlış mı anladım acaba? Angular bir distribution, probability distribution söz ediyorsunuz.
It might be, that's what I'm looking for. Is it possible to have some angular distribution? For example, is it possible to say that my particle is more probable to be over here? And is it possible that such a state is an eigenstate, for example? That will be one question that I will be asking eventually. Or another way of looking at this is, since we should have rotational symmetric systems, laws of nature doesn't change under rotations. That basically means h squared and ji, they commute. No, not h squared, h. So eigenkets of ji will be eigenkets of my Hamiltonian. I don't need to know what the details of my Hamiltonian are or what potential I have in my Hamiltonian. But still, as long as my Hamiltonian has rotational symmetry, its eigenvalues will be its eigenkets will be eigenkets of ji, some of them at least, and j squared. So basically, I'm looking at what are the possible eigenkets of the Hamiltonian. I didn't even specify, as I said, I didn't even specify what my Hamiltonian is. And can I say some general properties of my eigenkets of my Hamiltonian without specifying anything by just looking at the rotations? You see what I was saying over here in this argument over here just by looking at the rotational properties without knowing anything about my Hamiltonian, and if I consider some, let's say, some scattering process which conserves the angular momentum, let's say I have, at my origin, I have a spherical symmetric potential. And I'm just sending some particles, like in the Rutherford experiment, let's say. I can still say what the angular distribution will be. How the final state particles will be distributed angularly after the scattering. I don't even need to know what the Hamiltonian is, though. That's kind of what I'm trying to do now. Well, let's continue. Hopefully, when we do some more examples, it will be more clear why we are doing all these. Well, classically, we already know what the orbital angular momentum is. L is equal to R cross P. This is also what we use in quantum mechanics. Of course, promoting R and P to operators. Now, the first question is this Hermitian? You see, when you have the momentum and coordinates at the same time, they do not commute, and hence you might have some problems. For example, xp dagger is not equal to xp. Product of x and p is not Hermitian. So usually when we have products like xp in the classical system, that is why we write xp in the classical world. This is 1 over 2, corresponds to 1 over 2 xp plus px in quantum mechanics. So that we end up having Hermitian operators corresponding to quantities that are real in classical physics. Now let's look at this one. Lx is, what is Lx? Minus py and z. Ly and Lz is equal to xpy minus ypx. Well, you see, px is always multiplied with y or z. Px is never multiplied with x. Py is never multiplied with y. Pz is never multiplied with z. So everything commutes. So we don't need to worry about commutation. This R cross P is a Hermitian operator. Now let's look at the commutators. You see, if this generates rotations also in the quantum world, its commutators is fixed. It should still satisfy Li, Lj is equal to I, H bar, epsilon I, J, K, Lk. So it should satisfy If it doesn't satisfy these commutation relations, it doesn't generate rotations in the quantum world. Well, let's see. Let's start with Lx and Ly. This is equal to Lx is ypz minus pyz. Ly is zpx minus pzx. Well, the commutators of the first terms is ypx, pz, commutator with z. The second term, the first term and the second term over here, they commute. The commutator of the second term here and the first term here also commutes. And then we have the commutator of the second terms, py and x, z, pz. These are the only two non-zero terms in our commutator. What is the commutator of pz and z? This one. Minus IH bar. Py, z and px is IH bar. Minus IH bar or plus IH bar py times x minus y times px, which is nothing but Lz. So they seem to be generating rotations. But do they actually generate rotations? Now, let's look at how they act on a position ket. Let's assume that initially we have a state in the x, y, and z position. We have a ket which is localized at the position x, y, and z. And when we rotate it, it should be localized at the rotated point. Now, when we rotate it by, let's say, a very infinitesimal amount, we already know how the rotation acts. Let's just consider a rotation around the z-axis. So this should be 1 minus I over h bar Lz by some very small delta phi, x, y, and z. This will be equal to 1 minus I over h bar. Well, Lz, we had already said what Lz is. It's xpy minus ypx. Well, let me put the hats over here to denote that these are now operators. This is equal to 1 minus I over h bar xpy minus plus I over h bar ypx. Now, these are multiplied with delta phi. But you see, we had defined px, py, and pz as generators of translation. Now, this operator, we can write it as 1 minus I over h bar p dot delta r. X, y, and z, where this delta r is nothing but y minus y times delta phi in the x hat direction plus x times delta phi in the y hat direction. So this rotation operator acting on my ket x, y, and z, it just gives me, well, x is shifted by minus y delta phi, and y is shifted by y plus x delta phi. Z is not changed. It's my this state. So you see, if you would just look in the xy plane, if initially it was localized at this point, now it is localized at this point. X coordinate is slightly shifted to negative values, y coordinate is slightly shifted to positive values. But this is nothing but a rotation by delta phi. This angle over here is delta phi. So it does generate rotations for x, y, and z coordinates. So how would the spin enter into this picture? So we have generated rotations, no? With this r cross p. Let's also look at the possible values of L. You see what we know? Well, this is for an infinitesimal rotations. If you would just consider an arbitrary rotation by phi, you would just get, this will be x cosine delta phi, no, cosine phi, sorry, minus y sine phi, y cosine phi, plus x sine phi and z, which in particular means that if I rotate around the z-axis by 2 pi, I get x, y, z, no minus sign. Now, since there is no minus sign, this also implies that possible eigenvalues of L is 0, 1, 2, etc. No half-integer values are allowed, because half-integer values would just give me a minus sign if I consider a rotation by 2 pi. If you remember the spin 1/2, under a rotation around the z-axis by a theta, we didn't get cosine theta or sine theta, we got cosine theta over 2 and sine theta over 2. So that 2 was the reason why we had the minus sign. But here there is no minus sign. And hence we are not allowed to have half-integer values here. Now, how will the spin get into this picture? Okay, 10-minute break.